through recursion. And as we kind of defined, or I should probably define with you, recursion is the idea that we write a function that just kind of calls itself. And it does this thing that we needed to do over and over again until it reaches an endpoint. Now, at a high level, I think one of the bigger questions you might have had doing last week's workshop or doing the Recursion 1 workshop is, well, it feels a little bit kind of over-engineered, right? Like everything I'm doing there, I could easily do with a for loop. Sorry, really quickly, can everyone hear me right now? I just want to make sure that that people can't hear me. Hello, can you ever hear me? Oh, someone responded. Perfect, awesome. Okay, yeah. Sorry. So as I was saying, a lot of the recursion problems you probably worked on during the last workshop, you've actually might have even used a for loop in some cases to do it, and you might be like, well, this is so easy. Why would I ever use recursion, which seems tricky and difficult when a for loop does the same thing. And so for the workshops last week, that was correct. Every workshop there that you did more or less could be rewritten as a for loop problem. However, the reason why we do study recursion is because there are also another set of problems in which we are not able to do with a for loop, and we are only able to do with recursion. And so that will be the focus of today's workshop. So one thing that I'll caveat this lesson by saying is, generally speaking, if you find this particular lesson, it is our final one after all. If you find it to be particularly challenging, don't be intimidated. For the most part, on your assessment, you won't encounter anything that will be as difficult. That will be, I guess, I'll say, this difficult. And what I mean by that is, generally in our assessment, when we test you on recursion, the way we usually do it is we have you write a function that does something. If you do it very manually, we might say, well, how do you do it in a for loop? And then you write it with a for loop. And then we might also say, well, great. What if I didn't want to use a for loop? What if I wanted to use recursion? How would I kind of translate that function into a recursive function? And so that's usually the steps through which we kind of, that's usually the process through which we assess someone's understanding of recursion. I don't think, and don't hold me to this. I actually haven't looked at the assessment in quite some time. But generally speaking, we wouldn't give you a problem that can only ever be solved with recursion to say, hey, do this, and if you can't, then it shows you don't understand recursion, right? At the end of the day, recursion is a tool. You can choose to adopt it or not. And what we want to do is we want to figure out kind of how comfortable you are with it. And so all of this is to say that if today's session seems a bit difficult, or if this recursion session is a bit difficult, don't stress. It is more likely than not that your assessment will not cover recursion to this degree. Okay, so enough of the preamble. Let's get underway here. Recursion 2. Okay, so last week, or actually no, not even last week, maybe 2 weeks ago, we had this situation where if I wanted to print out every single element in an array, I would write something pretty much like what we see there on lines 1 through 6, right? I have a function, it takes in an array, I create my handy for loop, I go through every single element in that array, and I print it out. Nothing really difficult there. However, what becomes more tricky is, well, what if I want to print out every single element in an array, but now I introduce this concept of nested arrays, right? So on line 8 there, I see I have an array with only 2 elements. The first element is a number, pretty straightforward. The second element is another array, and that inner array has 2 numbers, 2 and 3. So now if I wanted to print out, now if I feed that nested array into the logs in array function, it only prints out 2 things. It prints out 1 and then the array 2, 3. However, that doesn't really help us, right? Because I want to print out 1 and then 2 and then 3. I want to print out every single number inside the array. And so I need to go one level deeper. Here's where this idea of recursion is really powerful. And so right now, if I look at what I'm doing here, I have my logs in array function. I'm going through every single element in the array on line 2 there. On line 3, I take out the element. And on line 5, I introduce a check. I go back to our handy array.isArray that we learned all the way back in array 1, and we check to see if the element is an array or not, right? Line 5 basically tells me, hey, is this element an array? If it's not, let's look at lines 8 through 10 first. If it's not an array, well, we just console log it out. We treat it like we normally would, right? We just print it out. We just console log it out. However, if that element is an array, notice how on line 6, that's where we recursively call ourselves. We say, well, if this element is an array, well, I need a function that is able to take in an array and print out every single element in it, which is exactly what we do. And so therefore, on line 6, when I recursively call logs in array on this inner element, it's almost like I am starting a new instance of logs in array, except this time I'm not feeding it the entire array. I'm just feeding one element in the array, and that element happens to be an array. So let's take a look at how this looks in practice on our call stack. On the first line, this is my initial call. I do that, and I print out. And then as I go through it, the first element, I know like on the in the call stack there, we just pretend like there's an array around the 1 and the 2, 3. So we're feeding in an array with 2 elements. In any case, as we go through the first element, which is just 1, we say, well, is array on line 5? Is that true or false? And it's false. So then we go to our else statement on lines 8 through 10. Okay, because it's false, we move on and we print out 1. So far, so good. On the next element, we say, is this array 2, 3? Is that an array? And the answer is yes, it is an array. Well, in order for us to solve that, we then need to call logs in array with an array of 2, 3. And notice how here, this builds on top of our previous call, right? Like this is where the way our call stack builds up. Once again, the reason why this is because I need to solve logs in array with the array 2, 3 before I can say I finished solving the array of 1, the array 2, 3, right? So once again, this is why the call stack builds up. It's just because now we're saying, hey, before I'm able to finish this, I actually need to do an entire other thing first. And as I feed the other array in, the 2, 3 in, notice how now if I look at my logs in array function, I now have a new instance in which I'm just feeding in an array with 2 numbers, 2, 3. So the first time I go through it, I'm looking at 2. On line 5, will give me false, it's not an array. So I go to line 8, 9, and 10, and it console logs out 2, and then it console logs out 3. And now my function is over. How do I know my function is over? Well, my function, once again, is just a for loop, right? The for loop, it iterates over I is less than the array.length. In this case, there are 2 elements in the array. This is 2, 3. And so when my for loop finishes, my entire logs in array finishes. And now I can, because I finished my logs in array function, I can take it off my call stack. And now I can resume where I left off previously with my initial function. Well, in my initial function, I was already on the last element, right? The array 2, 3. So there's nothing else we need to do there. That for loop finishes, and that iteration of the function also resolves too. And now I've finished going through every single element in this array, because I am able, at every single element, I'm able to check to see if the element is a nested element, in which case I will do a recursive call. If it's not, then I just print it out. Okay. Any questions so far? That should be a decently quick review of the recursion concepts that we've already covered so far in Recursion 1. Any questions? Okay, cool. So if I look at this problem, right, one of the things I'm kind of taking for granted here, one of the things I took for granted previously that I'm not taking for granted here is before, in yesterday's problems, if I give you a problem that only had 2 levels of nesting, if every element is either a number or an array, well, I could just write that with a for loop. But the reason why this recursive function is actually more powerful than the one we wrote yesterday is because there's actually no limits on how recursively deep we can go. Okay, and so this is kind of our introduction to a category of problems that can only be solved with recursion, not a for loop, right? Because if you imagine a for loop, right? If I tell you, the most nested array there is in this array is 3 elements, well, I can just write a for loop. I can write for, go through the first layer, and then another for loop for the second layer, and then another for loop for the third layer. But what if there's 25 layers or 100 layers? I mean, I guess theoretically I could just write 100 for loops, but even then, that depends on me knowing for sure that the deepest nested array is 100 elements deep, right? However, the way that we've written it here in this logs in array function is actually quite ingenious, right? What we're doing here is we're not really saying, hey, let me write a bunch of for loops. We're saying, let's just write one for loop, and then if the element is an array, well, we'll recursively call ourselves, and there's no limit to how deep we can go. But, and this is the key difference, we don't know how deep it will have to go, but it doesn't matter because this function will just keep going as deep as it needs to until it finishes, right? So if there's 5 or 6 layers of nesting here, well, at every single layer, we just keep saying, is this an array? Great, recursive call. Is this an array? Great, recursive call, right? We actually keep calling over and over and over again based on the data that we encounter, not how much we predefine, or not how much we define beforehand. And so this is the main reason why this is the kind of problem that we can write with a for loop, but we cannot write with a recursive, that we cannot write with a for loop, but we are able to write with a recursive function, right? Because a recursive function will just keep going until it reaches the end criteria. With a for loop, we need to always tell it before it starts how deep it needs to go, okay? So let's take a look at another example of a recursive function here. In this case, I feed in another array to my concat else function. And here, very similar to the last problem, I want to go through every single element, except instead of trying to print out every single element, I now want to add every single element and collect all the, in this case, every element will be a string or an array of strings. I want to collect every single element and then add it into one final string, okay? So let's take a look at how that looks here. I have my final string equals start, and then I have my for loop, and all it does is it goes through the array.length. I pick out every single element, and I just add the element to the string. And this works perfectly fine if the array that I'm feeding in has no layers of nesting, right? I do all this, I get back ABC. But if my array does have nesting, we need to go back and do what we did last time, which is now lines 1 through 4 are exactly identical. The only difference now is between lines 5 through 9. If the element is not an array, I go to line 7 through 9, and I see that here I'm trying to add the element to the final string. But, and this is super critical, right? If the element is an array, I not just recursively call it, but I actually care, not just I called it, but I actually care what the function returns, right? And what does the function return? The function returns all the elements in the array that I'm passing in added together, okay? So the line 6 there, like, you know, when you do the workshops, take a few minutes, just kind of like look at it and make sure you fully understand it, because this is the one part where I think people mess up on the most with using recursive functions, right? In a lot of cases, what you care about with a function is not just the fact that it was called, but you care about what that function gives back to you, okay? In this case, if I just call concat else with element and I don't add the final string, then it really doesn't do anything, right? Because if I call concat else, it returns a string that I don't store anywhere, and so therefore it's basically like I didn't really use it at all. Instead what I'm doing here is I go to final string and I say, hey, whatever the last call of concat else gave, give it to me and I will add it to the string that I currently have. Okay, and so the reason why we can do that is because if I look at line 2 and look at line 11, what I see is in my recursive function, every single time I run this function, I'm returning something, right? On line 2, I initialize it to be an empty string. On line 3 through 10, I'm adding things to that string. And on line 11, I am always returning that string back to whoever called it. And so this is why it's really, really critical on line 6. It's not just that we recursively call our function, but that after we call it, we actually take what it gives back and we store it, okay? And so now if I kind of walk through this code verbally, what we're doing is we're going through an array, and for every single element, if the element is a string, and I'm assuming everything is either an array or a string, if every single element is a string, then we just add it to our current final string, line 8 there, okay? That's pretty straightforward. However, if an element is not a string, if an element is an array, well, we just say, great, let's recursively call it. Here's an array. It's a subset of what I have, but here's an array. Tell me what string you get when you add all of those things in that array together, and I'll add it to what I have. I'll add it to my final string. And so at every single juncture, I guess if we put ourselves in the position of the function, right? We don't need to know how deep it goes. It's almost like peeling like an onion. Like we just peel one layer and we give the rest of the onion to the next person, or in this case, the next iteration of the function. That iteration will then peel the onion one layer and hand it off to the next one, right? In this case, we don't need to know how deep or how many layers the onion has. We'll just each keep peeling one layer and one layer and one layer, and just have the person next to us or the person underneath us do this, right? Same exact principle here. At every single level of the array, we'll go through it. If we find a number, we'll just take care of it. And if we find an array, we'll hand it off to the next person, right? We'll hand it off to the next iteration of the recursive call to deal with. And so if I look at kind of how the call stack looks for this, right? Initially, I have a concat else. I feed in an array with 2 elements. One is a string and one is an array of strings. I then add it to final string. I get back my A. And then when I go to my second element, I see, well, my array is array on line 5 triggers. And so therefore I go to line 6 and it says final string. Plus equal, right? So let's add what we have so far in final string, which is a letter A. And now let's add it to concat else. And then now we're going to feed in the element that we have that's currently an array, which is the array BC. Well, so now it says we need to figure out what concat else pass in BC is. Well, if I go through it in the first iteration, now we have a brand new iteration of this concat else function. We start once again with an empty string, and now we just care about this array BC, right? We don't care what happened previously. We just care about solving the problem that was given to us. In this case, the problem that's given to us is the array BC. So then I have an empty string, I add in the B, and I go to my second element, which is the C, I add in the C. Now I have BC, and now on line 11, I return BC to whoever asked for it, and this function is done. So then if I go back, so now I can move that iteration of the function off my call stack. I go back to where I initially called concat else BC, and I say, well, great. Let's replace our concat else with the string BC, and so now it boils down to A plus or equal BC. So we get back ABC as our final string. Okay. So that was kind of the way to handle it for nested arrays, right? And once again, right, just keep a note, right? Like the reason why this is not different, but this is kind of more powerful than what we talked about previously is in this application is if I give you a nested array and I don't tell you how deep it goes, it's theoretically not really possible for you to write a for loop that can go through every single element in that array because you don't know how many for loops to write. Recursion gets around that. Recursion just says, hey, I'm going to keep doing this. I'm going to keep peeling off one layer of the onion and one layer of the onion. And at some point, the assumption is we're going to reach the middle of the onion, right? We're going to finish undoing all the nesting. But I don't need to know how many layers there has to be or how many layers of nesting there is beforehand. Okay, so any questions on that? It's not anything new. It's just an extension of the concepts that we talked about yesterday or on Thursday. Everyone feels comfortable with this?
Yeah, I kind of feel comfortable with it, but I do have a general question of like when it's used, because I guess it makes it a little bit clearer for me if we know how and when it's used. I understand it needs to go deeper and deeper inside of each array to check on each element.
Mm-hmm.
Could you give me can you hear me?
Yep, I can hear you fine.
Like a real life example or something, or I don't know.
A real life example.
How you would use this, and because it makes sense.
Sorry, can you hear me? Oh, sorry, I think I might have cut out there. Can you hear me still right now?
Yeah, I can still hear you.
Okay, great. So I mean, I guess like I don't have a kind of a real world example handy. Like the example that we usually give is just like, hey, if I give you like an array and I don't tell you how many layers of nesting there is, like how would you add up all the numbers in that array? And that's like, I don't have like example handy, but like that's not a super common, but it's definitely an applicable like real world problem because a lot of times when people give you data, it's not good data. It's not very clean data, and you'd actually a lot of times you need to kind of go through it like very carefully. And so if someone just gives you a data set and says, hey, everything here is either a number or an array, how would you kind of parse it out? How would you get to the bottom of it? I mean, this is where recursion really comes in handy. In some of the workshop problems, we'll give you a few other examples of ways to use recursion. But I guess like I said, recursion is a tool and it's really powerful, but it's also not something that you'll be using very commonly, right? There's not like a ton of problems in databases that you'll do with recursion. Most of them you'll be able to do. Most of them you'll be able to do with a traditional for loop. So like the problems that we have, like the first one is to add up a bunch of numbers that are nested. The second one is to go through a bunch of objects, which we'll call as well. But it's, I'm sorry, but I don't really have like a handy like real world to kind of like, oh, like this is the classic way in which we use recursion.
No, no,
Yeah.
no. I mean, what you said exactly what I was looking for is like whenever you need to go through data and you can't just necessarily take everything for granted, you have to search through each one. That actually makes sense
Great.
because yeah, nothing ever
Yeah.
comes first.
Awesome.
Thank you.
Yeah, yeah. Cool. Any other questions on kind of this application of recursion? Cool. All right. Well, let's just wrap this up then. So the next example I'm going to walk through, it's the exact same concept, except now rather than dealing with a nested array, we're dealing with nested objects. Conceptually, the idea is still the same. Every single time I go through this, I'm peeling another layer of the onion. Except now, rather than removing one layer of the nested arrays, I'm now removing one layer of the objects or the nested object. Okay. So obviously, with arrays, we could do our for loop with an object. We don't really have this idea of a traditional for loop, but we do have our handy for in loop, right? Remember those from when we did objects. So here, if I was to say, hey, if I give you an object of key value pairs and every single value with a number, how would you add up all the numbers? It will look something like this, right? I start with sum equals 0. I go through every single key in OBJ, and for every single key, I find what the value is associated with that key, and I store in a value, and I add value to sum. And when everything's said and done, after I've gone through every single value on line 9 there, I return the sum. Okay, that's how I would do it for a single layer, normal vanilla object in which every value is a number, right? Nothing super fancy here. Now, obviously, the question becomes, well, what if we have layers of nesting, right? Then what happens? So if you look on the bottom there on line 14, yeah, like 14-ish. Notice how disgusting that object looks, right? We have a nesting. We have a nesting of a equals 1. That's fine. But for b, it's the value is another object, and then that b object has a key called c, and the value of c is in another object, and so on and so forth, right? And if you can tell, we just go pretty deep. In this case, it's 4 levels deep, but this could easily go much deeper if the data is bad. And so the question for us is, well, how do we add in that 1 and a 2 and a 3? And so if I look at my function here, it looks almost identical to what we had done previously with the arrays, except the main difference here, or actually only two main differences here, right? The first main difference is instead of using a traditional for loop, I'm now using my for in loop, right? And notice how the for in loop here still applies really well, because for in loop is something that we use when we want to go through every single key in an object or every single key and value in an object. And in this case, we want to go through every single key value pair in an object. So that means that the for in loop is very appropriate for us to use in terms of going through the object. And then now, rather than checking to see whether or not something is an array, on line 5 there, we're just checking to see if the type of the value is an object. Okay. Other than that, like our basic layout of the function is still the same, right? I start with my initial sum of 0 on line 2. On lines 3 through 10, I am adding numbers to that sum, and on line 11, I return that sum. When I do look towards adding numbers to that sum, if the type of a value is an object, then I'll come back to that. If it's not an object, then on line 8, I just add the value to the sum, right? That's very straightforward. On line 6, or I guess between 5 and 6, on line 6, what I'm really doing there is I'm saying sum plus or equal sum vals. And so what that's saying is, hey, I still need to add a value to my sum, but I can't add an object directly. So here, why don't I recursively call this function? I'll give you a smaller object, right? I'll peel the onion kind of one level deeper. I'll give you an object, and I just need to tell me what the sum of all the keys in that object is. And once you do, I'm going to add it to my sum, right? That's why it's sum plus or equal, this recursive call. And that inner function will do the same thing. If it goes through and everything's a number, then it'll just add it up and give it back to us. If one or more of those things is an is an object, then it will call itself and say, hey, I peel back the onion one more layer. Do you mind going in and telling me how much or what the sum is of all the number in the array? And this recursive function will just keep doing that over and over again until we reach a final state in which we go through the object. There are no objects. Sorry, we go through an object. All the values are numbers, and we just add it up and we return the value. And so if I go back to my handy call stack, here, if I go through the first key value pair, assuming A is the first key, we have our 1, pretty straightforward. Then we have our B, and the value for B is this, really hairy object here that we're now trying to solve for. So when we solve for that inner object, our initial sum is still 0, right? Because when we recursively call it, we start at 0. And then the value for this object is another really hairy thing, and another really hairy thing, and so on and so forth, until we get to the, in this case, final level of nesting. We have an object with 2 key value pairs, one's E and one's F. And so as you go through it, the first time it'll be 0 plus 2, and then 0 plus 3, and we get back a total of 5. And now we're actually able to kind of go back down our recursive call and saying, great, who asked for it? Oh, this person asked for it. Great, let's give them back 5. That person handles, the 5 and says, oh, great, my total is also 5. And so we pass it all the way back until we finally pass it back to the very last layer, in which it's 6. There's no other layers of nesting after that. So then we can say, great, we're done calculating this final object, and let's return back a 6. Okay, that was pretty much it, right? It's the same exact idea. Oh, sorry, same exact idea as the array, but now we're just using a for and loop, right? But the idea is still the same. Every single time we go through it, we're peeling it back one level deep, like we're peeling one level back, whether it be a level for a nested array or a nested object. Any questions before we start the workshop?
I had a question.
Yeah, go ahead.
So I've actually played around with recursion a little bit before, and I found that unlike using recursion with arrays to iterate through arrays or strings or numbers, can be pretty straightforward most of the time, when you try and iterate through an object, a nested object using recursion, more often than not, the behavior that you get can be a little unexpected. Probably because of the for in loop, because it has to go through the entire object. I'm going to try and give an example. It's a little vague, but hopefully it'll be clear enough. Like, I'm trying to see if a nested object has a certain value. And if it has that certain value, and I'm using for in loop with recursion, I want the function to return false, and I want it to stop. But what I found is that it will often not stop and keep on going. And if I'm trying to store that false into a variable that I set in the beginning, like sum, it'll often return, not false, because it goes through something else that's actually true and changes it to true, because the very end of the function is return that variable. Does that make sense?
I think, I guess, very straightforward. I think there's probably a mistake in your code.
No, right.
Yeah, like nothing that the way, like, recursion edited, it's a concept, right? It's like a way of thinking about code, really, rather than like an actual like physical thing. And so, like, the way that it goes through an object is no different than the way it would go through any other data type, right? Like, we easily use recursion on a string as well, right? Like, there's no difference between that. So if you have a code in mind, you can like kind of send it to me directly, and we can take a look at it. But there's no sense of like chance or like unexpected behavior in terms of conceptually what it does, for any data type. It should be doing the same exact thing.
Right. I'll try and kind of pinpoint in the question, make it more clear.
Yeah.
When I said expected, I meant that it didn't do what I expected it to do based on the experience that I had with arrays.
Mm-hmm.
And I guess the way the call stack works is that whenever the function hits another call of the same function, it goes one level higher in the call stack, and then runs that function again, halts the previous call of the function.
Yep, it definitely does.
So it returns whatever I asked it to return at the end, and then it puts it together with whatever I returned the call before, and so on and so forth. So that false that I was trying to get, if there's a certain value in my nested object, actually turned into true or into something else, because it was replaced with a true that had to come afterwards, because the for in had to keep going even after it got a return false.
Yeah, actually, that sounds very familiar to one of the workshop problems. It's going to be called All Systems Go. like that's I think at the heart of it is what you're trying to do there. So when you get to that problem, feel free to take a look, and then obviously we can like kind of walk through that problem too at the end of class
Oh, okay.
if folks find it particularly challenging.
Sounds good.
Cool.
Thanks.
Yeah, no problem. Any other questions on this on kind of I guess more recursion? Cool, awesome. Then let me get the workshop groups split up, and then we can get started. Like I said, this is meant to be kind of a challenging session. So if you don't feel like you don't get every single thing, don't stress. It doesn't mean that you're completely gonna bomb the assessment. Once again, we want to see how much you understand the assessment, but it's not meant to be like it's not meant to be like a like an all or nothing, like like very very